Well, welcome everyone to another TCS Plus talk. Before we begin, let me just give a shout out to the rest of the organizers, which are Clement Kanon, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, and Thomas Vedik. And just to remind you that also next week we'll have a talk by Ayush Jain. So hope to see many of you guys there. Okay, this week we're very happy to have Jayadev Acharya giving this talk. And Jayadev is an assistant professor at Cornell, where he's done a lot of very exciting work on both learning and testing. And today he'll tell us about distributed statistical inference under local information constraints. So please take it away, Jayadev.
Thanks, Eric, and thanks to the organizers of TCS Plus for inviting me to give this talk. I'll be talking about a recent line of research on distributed inference under local information constraints that we have been working on for the past 2 to 3 years. And our story begins 2.5 years ago at ITA workshop in 2018 when Clement, shown here on the left, who most of you know, and Himanshu Tyagi, who is at the Indian Institute of Science, and 3 of us, after the day, we went out for a drink, and not being nerdy at all, we decided not to carry pen or paper, anything. And inevitably, we ended up borrowing a pen from the bartender and started writing on the napkin that was provided with our drinks. And essentially, the conclusion of the day was that we have been working on the problems that we started discussing that day ever since. And I'll hope to give an overview of what we have been doing in this line in the past 2 to 3 years. And along the way, we have collaborated with several excellent students, Cody Freitag at Cornell, Yanjun Han at Stanford, Johan Liu at Cornell, and Zitang Son at Cornell. So Zitang and Johan are my students. Cody is at Cornell Tech, and Yanjun is at Stanford, as I said. So without further delay, let's dive into the main content. So what is statistical inference? We'll have a distribution P from which there are n IID samples x1 through xn that are drawn. And upon observing these n samples, we have to solve some inference task. Okay, I've not specified the inference task. We'll formalize it a little later, but there is some task about this distribution we have to solve given only access to the samples. And of course, the distribution P is unknown to us. And what's the figure of merit that we will use? So a common figure of merit is called as the sample complexity, which is defined in terms of the smallest number of samples n that you need to solve the inference task that you started out to solve. Okay. And that's the problem we want to look at. So what are the kind of inference tasks we want to look at? To define the inference tasks, we'll need one notation. And hopefully I'll keep the number of notations throughout the talk to a minimal and give the high level ideas. So epsilon will be the accuracy parameter that we will work with. It will denote basically how well are you solving the problem that you are trying to solve. And we look at 2 fundamental problems in statistical inference. The first is estimation, also called as learning, where the goal is to design a p hat. So you observe x1 through xn, and looking at these observations from the unknown p, you have to output a p hat such that the expected distance between p hat, your estimator, and the underlying distribution p is at most epsilon. And this d is some notion of distance between distributions. Okay, we'll specialize to some distributions later on, but this is the high level question of estimation. The complementary question for estimation is that of goodness of fit, also called as identity testing, where you are given a known reference distribution Q. So Q is known to you. And again, upon observing these n samples, you have to design a test T such that if the distribution P is equal to Q, such that, in other words, P is equal to the reference distribution, then with probability at least 0.9, you have to output 0. And if P is at least epsilon away from Q, again, it could be the same distance as before, or it could be any other notion of distance, then you output 1 with probability 0.9. And 0.9 has been chosen arbitrarily. So it's just some high probability. Okay, so those are the two questions we will look at during this talk. Okay, so the title of the talk contained under local information constraints. So what are local information constraints? Okay, so the setting that we talked right now is when you have access to all the samples, but in many practical applications, you will have only limited information about each of these samples. So even though there is a distribution P that generates X1 through Xn, you'll not be able to get access to all of these Xis. Let's look at a couple of examples. One is communication constraints, where each of these samples Xis must be expressed with L bits. So you get these Xis and you have to quantize it up to L bits. And that's the observation that you get to see. You don't get to see the original Xis. And another application is for local privacy constraints, where the Xis can denote some sensitive information about users. So each of these Xis may be data that's held by a user, and they denote something about the user. And they don't want Xis to be leaked, so they want only a privatized version of Xis to be available. Okay, and you could have other problems. So in this talk, we'll focus on mostly communication and privacy constraints, but you could have other examples such as the linear measurements, where each of these Xis could be a high dimensional vector, high dimensional observation, and what you see is a projection of Xis onto a smaller subspace, let's say. Okay. So with this in mind, how do we model these information constraints? So you have Xis, you don't get to see Xis, instead you get to see some limited information about the Xis. Let's see how we can model these local information constraints. So what we can think of is these are n samples that are distributed across n players or n users, and user I observes Xi. So each user observes one sample, and you can think of the limited information that you observe about the ith sample is a message yi that the user I sends. Okay, so in other words, we can capture this through this picture that I'll show. To define that, we will need one more notation, which is this calligraphic X, which denotes the input domain of X. So we said T is an unknown distribution, and that distribution is over a set X. Okay, and the way the local information constraint of user I works can be expressed through this box, which is a randomized mapping from X to some set. So this Wi is basically, we'll call it as a channel. And this Wi is nothing but a probability distribution of output given input. It's a randomized mapping. So Wi of y given X basically denotes the probability that the output yi is y if the input Xi is X. Okay, so each user is going to take Xi and pass it through this channel Wi, and the output yi that you see is the message. Okay, we'll give a couple of examples in the next few slides why this is a generic notion that can capture all the constraints that we saw before. Before we do that, so W is just a probability transition matrix from X to Y. That's it, nothing more than that. So once you have Wi, let's say the Wi for the user I is fixed, then what is the output distribution of the messages? That will have this simple form. So the output distribution, the probability of output message being Y, is basically sum over X, P of X. P of X is the distribution of X times the transition probabilities. That's it. Okay. So now the way we are going to model these local information constraints is by considering a set script W of allowed channels. So you cannot choose arbitrary Wi's. You will be given a set of channels from which each of these Wi's must be chosen. Okay, let's see why that makes sense. Let's take one example, which is communication constraints. Here, the script W is given with W subscript L, which is the set of all channels W whose input set is X, but the output set is L bit string. So this is a case where each of the Xi's is mapped to L bits and hence captures the communication constraints of L bits. Okay. And similarly, local differential privacy, which I think has become very popular in the past decade, is this set of channels. And let me just describe it. Hopefully several of you have seen, otherwise hopefully this will clarify. So a channel from W is a channel, which is just again a probabilistic function from X to the set of all binary strings in this case, is called rho LDP. And I think most of the people in differential privacy like to call it epsilon local differential privacy, but unfortunately, this epsilon for accuracy has been used way before LDP became popular, I can say. So I apologize for that. So W is called as rho local differential private if W of y given x. So you pick any y as the output message, and for any two possible input messages, inputs x and x prime, W of y given x divided by W of y given x prime is at most e to the rho. So what does it mean? It means that basically looking at y, you can't say for certain what the input x was, regardless of what the y is and what the input might be. Okay, that's what this notion tries to capture. And one thing you can see is if a rho is a very small number, then it becomes harder and harder to tell about the input looking at the outputs. Okay, and the W rho will denote the set of all possible LDP channels. Okay, are there any questions about until now?
Yeah, there's a question in the chat. So
yes.
G of x prime is not necessarily 1 in this setting. I guess in the central differential privacy, you look at x and x prime being neighboring.
Yes. So we do not have a notion of a data set here because we are assuming that each user is getting one sample. So each of these small x and small x prime is the data that one user has. So each user has exactly one data point. And when they give you a message about that data point that they have, they want to preserve its privacy. That's what this definition is trying to do. Okay. So in some sense, it is there is a notion of the distance between x prime is basically 1 if x is not equal to x prime. Okay, I hope that clarifies the question. Okay,
Thanks.
so with that in mind, we can actually pictorially represent what the setting is. Our distributed statistical inference can be seen through this picture where there is an unknown distribution P that generates x1 through xn. You don't have access to x1 through xn. Each of these xi's is passed through a channel, and the output of the channel is what you get to see. So there is a referee R that gets to see these output messages. And upon seeing these output messages, it has to solve the same tasks that we wanted to solve before. Okay, of course, the task will become harder. So the sample complexity will, of course, become bigger. Okay. So let's look at a little more of the math. So suppose we fix the set of channels that the users use. So in other words, we have these n users. Let's say the scheme that each of the user uses to map the input xi's to the messages is fixed. Once W1 through Wn, the channels are fixed, the output distribution can be written as the product of product over each of the users, probability of the output of the users. Why? Because as you can see from this picture, the xi's are IID. If the xi's are IID and w's are fixed, then the output messages are also independent. Okay, because once you fix the w's, the output distribution is exactly defined by this expression. Okay, so in fact, the most interesting task here would be how to choose the w's. In other words, if you are doing privacy, how do you privatize, or what kind of schemes do you use to privatize your data set? If you are doing communication constraints, what's the best way to map the messages that you have into L-bit strings? Okay. So now that we have this as the problem, so the whole problem is now how do we choose WIs that belong to some set script W that we know to achieve the sample complexity. Okay, so now let's see what is the amount of freedom that we have in choosing the W's and how that plays in that will play a role in the several tasks that we will look at. Okay, so the first kind of protocols, which are the simplest, are called as the simultaneous message passing protocols, where all the WIs, all the channels are chosen simultaneously. So in other words, there is no interaction or nothing. The WIs are chosen at the same time. And as we said before, once the WIs are chosen, nothing else matters. Okay. So even within this, there are two kinds of protocols that can happen. One is called as private coin simultaneous message passing, where the WIs are independent of each other. One example could be where WIs are all fixed a priori. Okay, so each of the channels at each of the users is fixed beforehand. And when this happens, as I said before, the outputs YIs are independent. Okay, And the counterpart of this is called as public coin SMP protocols, where there's a randomness U. There's a public randomness U that's shared across all the users and the referee. And the channels that, that are chosen by the users can now be a function of U. Okay, so, then you can see that once you know U, your channels are a function of U, and once the channels are fixed, the output messages are independent, and therefore the output messages are independent given U. Okay. Pictorially, we can represent it like this. So it's the same picture as before, but now there is this public randomness U that's shared across all of these players and the referee, and these WIs are now a function of U. Okay. So these are simultaneous message passing protocols. Of course, can come up with much more general class of protocols. One of them we'll look at is called sequentially interactive protocols, where there is a notion of time, and the player I chooses its WI, or the way it's going to quantize or provide the limited information about its symbol, is based on U, the public randomness, and on all the previous messages that have been sent. Okay. So pictorially, it can be represented like this. You have U as before. And now if you look at W2, there is this blue line that goes from Y1. So W2 is chosen after looking at Y1. And similarly, when the last player chooses its channel, it gets access to all the previous messages that have been sent. Okay. Are there any questions about the setup? Okay. All right. So what are some of the pros and cons? So if you look at just the implementation overhead, it's pretty clear that private coin SMP protocols are the easiest to implement, because imagine that these players are actually some kind of chips or sensors, and you want to sense some observation and only pass a limited information about it. It's the easiest if you could a priori fix the sensors, let's say, or how they do the mapping. And public coin SMP is slightly more complicated, because they have to all agree on a shared randomness. And interactive protocol, on the other hand, will have a lot more overhead, because you have to do this sequentially. So it will incur a lot of latency, and also implementation wise, there could be other problems. But then the question is, do you actually gain? Because we saw that, okay, interactive protocols, you have a lot more information when you are choosing the channel. So what is the advantage that you might get if you allow for interactive protocols in these statistical inference tasks? And that's the question we will try to answer in this talk. What's the sample complexity for the basic problems of learning and testing under private coin SMP, public coin SMP, and interactive protocols? Okay. Are there any questions?
Yes.
I think, yeah.
Jayadev, I have a question.
Yes.
So when you say interactive protocols, is it allowed to, say, go through multiple rounds of
That's
this?
a great question. So we are not going to look at it, but those are called as blackboard protocols, where you are allowed to go over multiple rounds over the dataset, but we are not going to look at it today. Yes, those are called blackboard protocols, and there is some work on it. Okay, but as you can see, even interactive becomes hard to handle. So, okay. All right. So now let's see, let's go back to our, this is the same slide as I shared before, except I'm just writing that instead of x to the n that you observe, this blue, in blue we have y to the n, so that you have to solve the same tasks of learning and testing, but now observing y to the n instead of x to the n. Okay.
There's a question.
Yes.
So is there a meaningful analog, something that is not necessarily a statistical estimation task?
Wait, I'll try to read the chat. Is there a meaningful analog? Oh, that's a good question. So imagine you have and that's a very good question. So you could ask these questions where imagine these xi's are actually fixed, is a fixed string, and you want to estimate, let's say, the heavy hitters, like which are the xi's that appear most frequently, and can you do this in a under communication constraints or under privacy constraints? So yes, those can be meaningful questions, and there has been work on those. I hope that answers the question. Okay, so moving forward, let's describe some of the results that we have obtained over this past 2 to 3 years. And the first set of results will be concerning a k-array discrete distribution. So where basically the underlying distribution is over a discrete alphabet of size k. And we have 3 papers on this in the last cohort, ICML and AI stats on various aspects of the problems, and I will cover each of them in detail later. And we also recently published a paper on these problems with in the interactive setting where you allow for sequential interactiveness. And we have also been able to work on to do this to consider these local information constraints for high dimensional distributions such as a Gaussian distribution or product Bernoulli distribution under general LP losses. And in Colt 2020, we looked at the problem of detecting whether, so you are given samples from a Gaussian distribution and you want to know, is the mean equal to 0 or is the mean away from 0? So this is basically detecting signal versus noise in signal processing. And we want to do it under limited communication from each of the signal. Okay? And as recently as less than 24 hours ago, we uploaded this paper on interactive estimation under for these high dimensional distributions under information constraints. So we have come up with general ways of proving lower bounds for high dimensional distribution estimation under let's say privacy and communication constraints. Okay, so that's available here, and you can go to the link. Okay, so in today's talk, what we are going to do is to talk about k-array distributions. But before that, let me talk a little bit about related work. And there is a ton of related work on machine learning and distributed inference. But the list is too big, so I won't be able to do justice to all of them. So what I will do in this slide is to talk about the results that are directly related to the technical content of this talk. Okay. So for learning under communication constraints, there are a few other papers. So Han, Osgur, Weisman, and Barnes, Han, and Osgur around a similar time as us looked at the similar model of distribution estimation under communication constraints. Diakonikolas, Grigorescu, Lee, Natarajan, Onak, and Schmidt, they look at a slightly different model, and this was in NeurIPS 2017, where they look at the total amount of communication and try to come up with sample complexity bounds where you don't have local information constraints. So this is something like global information constraints, although it's not entirely, that's also not entirely correctly characterizing the results. So for testing under communication constraints, there are a couple of very interesting works, one by Fisher, Meyer, and Oshman, where they look at a slightly different focus with multiple samples and do slightly different things. For this paper of Andoni, Malkin, and Shekel, they look at two players, which have basically one of them gets the samples and the other one has access to some other things, and how they can communicate with limited communication and solve various kinds of questions, various kinds of statistical inference questions. Okay. The one that has been studied a lot in the past few years is the local privacy, where, for example, for local private learning of discrete distributions, there has been many approaches, and this is just a list of all of those works. For locally private testing, we have works that started with Sheffet, and this year there have been two very nice works by Amin Joseph Mao and Barrett and Buttigia. One, I think Colt one will be in NeurIPS this year. And they look at some problems like what we will do. And I'm going to discuss the related works in the context of each of the problems. But I think decentralized, understanding these problems in a distributed setting has a long history. I think Tsitsikilis way back in the 80s and Varshny around that time, they have looked at these problems for signal processing, and they have really a set of amazing results, which can be form the basis of some of what our motivations are. Okay. So with that, let me start talking about our formulation. Okay. So our formulation is the following. We will consider discrete distributions for most of the talk, and we will consider the P to be an unknown distribution over a discrete set of size K. And for simplicity, we will assume that the set is 1 through K. So we have distributions over integers 1 through K. And the notion of distance that we will look at for most of the talk is called as the total variation distance, which is basically half of the L1 distance. And this is the precise definition. So we want to estimate distributions and test under L1 distance or under total variation distance. Okay. And with this, I think the two tasks that we have is, the first is estimation. You want to estimate p hat, estimate the underlying distribution with a p hat so that the expected total variation distance is at most epsilon. Okay. And for the goodness of it, we are going to specialize to the case where the reference distribution Q is the uniform distribution. So U denotes the uniform distribution over the K element. So probability of each of the element, each of the symbols I under the uniform distribution is exactly 1 over K. And we want to know whether the unknown distribution P is the uniform distribution over the discrete set, or if it's away in a total variation distance. And testing uniformity is in some sense the hardest possible problem, and that's why we are looking at it. But I think for now we can be motivated enough to just look at uniformity. Okay. So with that in mind, let's see what we know about the problems. Okay. So of course, these are very basic problems. So people have looked at it for a long time. And when you do not have any information constraints, so in the setting when you actually get to see the exercise, in the centralized case, the sample complexity of estimating the distribution or learning is K over epsilon square. And in fact, you just take your observations and output the empirical distribution that you see, and that achieves this K over epsilon square. And for the lower bound, and this is also optimal, so you do need K over epsilon square samples. And for the lower bound, there are many proofs, and the most classic one is through Fano's inequality. Okay. For the problem of testing, the optimal sample complexity, instead of being K over epsilon square, becomes square root K over epsilon square. So in some sense, it's an easier task. And there are many different estimators that achieve this. In fact, you can probably trace back to Walt's results back in the 40s and then try to develop on it to come up with several of these schemes. Okay. And lower bound is achieved through Leckam's two-point method, and this precise lower bound of square root K over epsilon square was proved by Paninsky, and we are going to use some of those constructions later in the talk. Okay. So let's dive into communication starved setting, and that's where we are going to spend a little bit of time. Okay. So let's recall the communication constraints. So here we have the set of channels that you are allowed to use to enforce the communication constraints is given by the set of all mappings from K, your underlying set from 1 through K, to L bit strings. Okay. So WL is the set of all channels that takes K that goes from K through 0, 1 to the L. And we can assume that L is at most log of K. Okay. Why? Because if L is at least, once L is equal to log K, you can actually send the exact input symbol that you have. So each of the WIs can become identity. In other words, you can come up with a channel that can represent the exact input that you have once you have enough bits. And the number of bits is exactly log of the domain size. Okay. So what we want to do for this communication constraint is our first overarching goal, and this was actually the problem we started discussing during that first night that I started talking about, is a distributed simulation problem. And the way I can state it is the following. So let's forget about all the inference tasks. Let's try to come up with one approach that can probably solve all the problems. Okay. And we call it as the problem of simulation. And what is the question there? The question is, imagine the referee could see these L-bit messages, and upon looking these messages, suppose it could somehow simulate samples from the underlying distribution. Okay. It may not know P, but it can simulate the samples. Then it can solve any problem that's solvable in the centralized setting, maybe with a much higher sample complexity, but technically it can solve it by just simulating samples by using enough users. Okay. So therefore the question becomes, how do you simulate a sample from P by using L-bit messages? So pictorially it's this, you want to, so the goal here for the referee is to output this X whose distribution is exactly P. Okay. So why is this an approach to solve everything? Because once you can simulate, so if you have an algorithm that can simulate one sample from P using T users or T players, then you can solve the centralized task. You can solve a centralized task whose sample complexity was S with S times T players. So you can generate S samples by using S times T players and solve whatever you could do in a centralized setting. Okay. So now the question is, how do you solve it and if it's solvable? And this was one of the results that we came up with. And there is, so in fact, there is a private coin simultaneous message passing algorithm that can simulate a pure sample from P that uses K over 2 to the L players in expectation. Okay. I'll not discuss too much about the expectation part, but let me just clarify a couple of things. So imagine L is log K. Imagine you do have log K bits. Then how do you simulate? The first player gets a sample, tells you what the sample is using the log K bits that it has. You're done. So you can simulate with one sample. With one player, you can simulate one sample. But when L is 1 bit, so if each player could send just 1 bit or very few bits, then the number of players you need to perform the simulation task grows linearly with K. It can become K over 2 to the L. So as a corollary, there is a private coin SMP algorithm where each player sends L bit messages that can solve any centralized task with S times K over 2 to the L players. So there's a blow up of K over 2 to the L in the sample complexity where S is the centralized sample complexity. Okay, I hope you're all with me, and if there are questions, please feel free to ping. Okay, so what I will do in the next slide is to basically give you a sample of how this simulation protocol actually works, okay, for L equal to 1. So I'll try to instantiate a lot of our works with just 1 bit communication, okay. So let's look
just
at yes.
Just a small clarification. So here for the simulation problem, there is no epsilon, right? It's
there is no epsilon. We are trying to generate a sample exactly from P. There is no epsilon. You want to generate a pure sample from P. Yes.
And
so
there's another question. So there's a question asking, how does the centralized algorithm works in the local privacy setting?
That's a good question. So we are so in the communication protocols, the way we are going to do so in local differential privacy, there is no notion of a centralized algorithm in some sense. So I think this part about simulation is restricted to communication constraints, and in fact, you can show that you cannot simulate a pure sample in the local differential privacy setting because of the way the channel is designed. So communication channels are somehow nice in a way that you are able to generate pure samples from the underlying distribution. Okay, so let's look at the protocol for 1 bit communication. So each player is going to send exactly 1 bit. Let's see how we can simulate a sample. So let's recall that our distribution P is over a set 1 through K. And the way we'll do it is start with a block of 2K players. Let's call them X1, X2 up to X2K. And what we'll do is the ith block is going to just look at their sample, and each of those players will just tell you if their sample is I. So the first 2 players will say, is their symbol Y? So X1 will tell if their symbol, if X1 is 1, X2 is 1. Similarly, X3 is 2, X4 is 2, and so on. So you can mathematically write it like this. Okay. So this is the 2K players, and the 2K players will send these as their 1 bit messages. And upon observing these messages, the simulation protocol is the following. You are going to output I. Okay, I is a number between 1 through K because you are trying to simulate a distribution that's over 1 through K. If user 2I minus 1 is the only odd player that's sending 1. Okay, so you have all of these odd players, only one of them sends a 1. And that corresponding user number 2I sends a 0. Okay, if this happens, you are going to output I. If there is no such I, then you are going to output failure. Very good. And the claim is that conditioned on not outputting failure, your output is actually a pure sample from P. Okay, and this is a nice exercise. That's why I wrote it this way, that you can go back and write and verify that it's true. Okay. And therefore, with about K samples in expectation, we can simulate. And now L is 1. So therefore, with a blow up of K, you can perform any centralized task with 1 bit of communication. And of course, you can extend it to L bits, but I will not show that. So what is the implication? Here is the implication for both learning and testing in one picture. So with L bit communication constraints, with a private coin L bit communication constraint, so there is no public randomness because of the way our simulation algorithm worked. such that with a blow up of k over 2 to the L, you could solve both learning and testing. Okay, let's look at one example here with L is equal to 1. That's how I'm going to motivate some of the work. So when you substitute L equal to 1, you can do learning with 1-bit communication by using k square over epsilon square users. So there is a blow up of k. Similarly, you can do testing with k to the 3 over 2 players. So you just substitute L equal to 1. So now, okay. And in the centralized setting, you can do testing with square root k, okay. So now the question is this scheme optimal? Is simulate and infer scheme optimal? Turns out that yes, this is the best you could do. There is nothing better to do. And we are going to see more details later in the talk. But when you are, and that's for learning, but for testing, it turns out that you can do better than simulate and infer. So instead of trying to simulate enough samples, you can actually do better when you have public coins, okay? And this is the main result that we have. So if you have L bit of communication per player and you have access to public coins, then you can solve the same problem of testing with a blow up of square root k over 2 to the L. Instead of k over 2 to the L, now the blow up is square root of k over 2 to the L. Let's try to just look at it for L equal to 1. So, and the second block is basically for simulate and infer that we just talked about. So you can do better. And what happens for L equal to 1 is simulate and infer tells you need k to the 3 over 2 over epsilon square samples. With public coins, you can do with k over epsilon square. So if you just substitute L equal to 1 in the first equation here, you get k over epsilon square. So that's an improvement of square root of the domain size. And in the centralized setting, you have square root k over epsilon square. So these are the 3 benchmarks. Okay. Are there any questions about this? Okay. So let's see how our public coin SMP protocol will work. Okay. And again, let's recall that in public coin SMP, you actually can synchronize the channels. So there will be a public randomness U that will be seen by all of the users, and they choose their channels depending on this public randomness, so they can synchronize. So it's not simulate and infer. And let's see how the synchronization can help. And here is the way.
Sorry, just to reiterate on that model. So U is common to everybody, but it's independent of the inputs. There's like no relation between the samples and.
So it's like this. Each of the users get U, okay? And after getting U, so P is fixed, but then U is independent of the Xis. Yes, U is independent of the input samples. Otherwise, you can actually show that if U is dependent on the input message, you can show that LDP will not be LDP anymore. But that's a side note. But yes, U is independent. It's just shared randomness, just generated independently. Okay, let's see how it works. So let's come up with the algorithm that actually gives us the k over epsilon square public coin testing algorithm. Instead of the k to the 3 over 2 that simulate and infer will give, let's see how we can get a k over epsilon square algorithm. It's actually pretty simple. You use your public coin to generate a random subset of the domain k with size exactly k over 2. So let's assume that k is even. Okay. So the public randomness is used by all of these players to agree on the same set S, whose size is k over 2. And what do each of the players do with their 1 bit that they can communicate? Player I is going to just look at its symbol xi and see if it belongs to the random subset S, it's going to send 1, otherwise 0. That's it. So they send indicators of whether their inputs belong to this set. And when now you can see that when the underlying distribution is uniform, recall that you want to test for uniformity. You want to test if the underlying distribution is uniform or not. When P is uniform, then the output messages are Bernoulli half distributed. Why? Because probability of half of the set is the probability of S under uniform distribution, which is exactly half. Okay. And now comes the slightly more interesting part is this lemma that we proved, which is that if you have a distribution P, and this is the alternate case, that's at a distance of at least epsilon from uniform, then with probability at least a constant, and under the randomness over S, P of S is at least epsilon over 4 square root k away from a half. So you have two distributions, P and U. over the domain K. And now you are doing a randomized mapping to a smaller subset, in fact, to a binary subset in this case. You're mapping distributions to binary alphabets. And it turns out that if P and U are far away, then a randomized mapping will somehow preserve their distance also. So this is in some sense a one-bit isometry, and we discuss how you can do these problems with the least amount of public randomness in a paper in Colt this year, where we characterize exact number of bits of public randomness that you need to solve this problem. But that aside, what this tells you is it's in some sense like a Johnson-Linden-Strauss kind of result. You have P and U that are far away in total variation distance in some large domain alphabet. You project it onto a smaller size alphabet, and if the distributions are initially far, then they will be far after projection also. Okay. So this requires some Paley-Sigma following with the careful analysis. But now the problem reduces to this, right? You are given these messages which are 1-bit messages. When the distribution is uniform, it's Bernoulli half. When the distribution is not uniform, then it's at least epsilon over 4 square root K away from a half. Okay. So now the question becomes how to test bias of coins. Okay. And here is the question. How many tosses do you need to decide if a coin is fair or has bias at least epsilon? Is at least half minus epsilon or half plus epsilon? And the answer to that is 1 over delta square. That can just work out with basic probability. And for us, this delta is actually epsilon over square root K, and that's what we saw here, this epsilon over square root K. And once you plug epsilon over square root K, 1 over delta square becomes K over epsilon square. Okay, and therefore, now you have a public coin SMP algorithm with K over epsilon square samples, 1 bit per player, not 11, 1 bit per player, and simulate and infer with K to the 3 over 2 over epsilon square. Okay. So now these are the set of all the upper bounds that we could obtain until now. Okay. For learning, you have a blow up of K over 2 to the L, and that's also for public coin learning. For testing with private coins, you have a blow up of K over 2 to the L, and with public coin, you can reduce it to square root of K over 2 to the L. Okay. So now, before we talk about lower bounds, so this is essentially what all the upper bounds that we wanted to present about communication. And hopefully these upper bounds were themselves interesting. And the paper by Hanosgur and Wiseman, they have a different, or they had a different algorithm for the L-bit communication scheme, which is in the paper that's listed in the references. So before moving on to the lower bounds, let me just say that for local differential privacy, there is a striking parallel between communication and privacy. Okay, and in my mind, or I think hopefully by now, all of us, at least Himanshu, Clement, and all of us think of local privacy and communication to be essentially the same thing with a different set of channels. Okay, and let's just recall, local differential privacy is where looking at the output message Y, you cannot say whether the input was X or X prime up to a factor of e to the epsilon. Okay, and we will be interested in the case when rho is a small number. Okay, is order 1, or let's just think of rho as 1. Okay, so we are in this setting that's called as high privacy. Okay, so there's a lot of noise that has to be added. This is the only slide that I will have about upper bounds for local differential privacy. Okay, and I do not know why I still have this L-bit private and L-bit public, which should be rho LDP. Okay, this is not. I can't really say that I was sloppy. I've spent quite a lot of time in reorganizing the slides, but this still, no matter how much you do, something slips away. Okay, so here are the upper bounds for L-bit for rho local differential private testing and estimation. Okay, and for learning, similar to communication constraint, there is actually a blow up of K over rho square. So previously in the centralized setting, you could solve the problem with K over epsilon square samples. You could learn the distribution. Now you need K square over rho square epsilon square samples. Similarly for testing without public coins, so you have we have local differential privacy, but without public coins, you have a blow up of again K over rho square. And similarly, we can come up with another algorithm that looks similar to what we did for the 1-bit protocol before, which actually shows that you can do public coin testing. You can do testing under local differential privacy when you have public coins available with a smaller blow up, the blow up of square root k, just like before. Okay. And learning upper bounds, there are many papers, as I had said before. There is a list of them. And testing upper bounds, they started with a work by Orr Sheffet, and in our work, we basically closed all the gaps that was there in their work, and we also provided tight bounds for both public and private coins. Okay. So now we come to the last part of the talk, which is about optimality. Okay, right now we were talking only about protocols, and at least we think that the optimality and the lower bounds are the more interesting contributions that we have to make. So here is the claim about optimality. Our theorem is that all the upper bounds that we have presented are tight for both private coin and for both privacy and communication, both private coin SMP and public coin SMP. So we have looked at only at simultaneous message passing until now, okay, as you may have noticed. So what's a corollary? First corollary is that public randomness or public coin SMP helps for testing but not for learning, okay, because all the upper bounds are tight, as I said. Another interesting corollary, at least interesting for us, is for the tasks of learning and testing, simulate and infer is the best private coin SMP algorithm that you could come up with under communication constraints. Because those bounds were tight, simulate and infer is what you should do if you don't have public coins. Okay. And for the lower bounds, I'm going to provide a unified approach based on this notion of chi-squared contraction that we have. Okay. There are any questions? Now is a good time to ask. Okay, so before we go into lower bounds, let me just recap some of the lower bounds that were proved either independently, simultaneously, or before us. So for communication constraints, I said the lower bounds that we are going to discuss is from this paper ACT 19-1 for the two papers that we have in 19. And there was another approach for Han, Mukherjee, Osgur, and Wiseman. Both of them provided upper and lower bounds for communication constrained SMP protocols, okay, only for communication, and for privacy, and this is only for learning, okay. And for testing, I think our work is the only one that has the lower bounds for optimal lower bounds for testing under SMP. And for the lower bounds for learning under local differential privacy, you want to do distribution estimation. There were a number of different works that came up with lower bounds. There was a paper by Ducci, Jordan, Wainwright in 13 that proved lower bounds for simultaneous message passing protocols. The paper by Ye and Barg, which looked at private coin SMP and proved lower bounds, except they looked at the entire range of rho. Rho could be small or big, whereas most of the other works look at a constant rho. And we provide SMP lower bounds for in a unified way that looks at both privacy and communication as two sides of the same coin, and also gives us optimal bounds for testing. Okay. So now, with that in mind, I want to now move into how to prove optimality, and hopefully this will be interesting. Okay. So to prove optimality, let's first look at public coin simultaneous message passing protocols and try to come up with ways of proving lower bounds for it under information constraints. Okay, so the biggest message that I want to give is how do we characterize how much information is being transmitted about the true input after you apply these local information constraints. If I'm giving you only one bit, what is the information about the sample that you are able to send, and what is the most amount of information you can send? If we can characterize it, then we can prove the lower bounds. Okay, so that's what we'll try to prove now. So to start off the problem, instead of looking at discrete distributions over the entire simplex, we will restrict to a small set of distributions, which is basically the method of Inkster that was introduced in '86. And this particular instantiation is by Paninsky in 2008 when used for uniformity testing lower bounds. So we have a set calligraphic P of distributions. It consists of 2 to the power k over 2 distributions, which are indexed by a binary vector of size k over 2. So you take a plus minus 1, a Rademacher vector of size k over 2. And for every such vector, you have a distribution, and the distribution is given by this, and I'm going to pictorially motivate it. That's all I will do. Okay. So suppose you take a string z1 through zk over 2. Suppose z1 is 1. When z1 is 1, then probability of symbol 1 is 1 plus 4 epsilon over k. And the probability of symbol 2 is 1 minus 4 epsilon over k. Similarly, z2 is 1. Therefore, symbol 3 is probability 1 plus 4 epsilon over k. And symbol 4 is probability 1 minus 4 epsilon over k. And z3 is actually minus 1. So symbols 5 and 6, the flip. Symbol 5 has probability 1 minus 4 epsilon over k. And symbol 6 has probability 1 plus 4 epsilon over k, and so on. So notice that the sum of all the probabilities will be still 1. And once you have any z1, z2 up to zk as a plus minus 1 vector, that gives you a corresponding distribution. Okay, so now you have a set of these 2 to the k over 2 distributions around uniform, okay, such that the distance of any of these distributions is exactly epsilon away from uniform. Okay, so you have constructed this set of instances, and now we are going to try and solve the learning and testing tasks restricting to this distribution. So instead of looking at all possible distributions we want to learn, if we can show that, oh, you can't even learn distributions if I tell you that they belong to this family P, then that will be a lower bound for both learning and testing. Okay. So let's see how what the approach will be. And in the slide, I would like to basically tell you how we are going to prove the lower bounds. Okay. So for learning, we are going to just show that if I give you a distribution from this 2 to the k over 2 distribution, still you need a bunch of samples, and that will be a lower bound. For testing, what we will do is we instead of looking at the entire space, we'll say that either the underlying distribution is uniform, or what I'm going to do is to pick one of these 2 to the k over 2 distributions from P and give you some, and that will be my P. Okay, that will be the underlying distribution. And with that in mind, what we can do is in the second case, when you are drawing a distribution from uniformly at random from this class of 2 to the k over 2 distributions, the output distribution of the messages is exactly given by this expression. So with you are picking one of these distributions at random, one of the 2 to the k over 2 distributions. That's the 1 over 2 to the k over 2 factor in the beginning. And once you fix the distribution, once you fix the z, the output distribution of the messages are fixed. That's given by pz w to the n, y to the n. Okay. And now Lecam's 2-point method, it tells you this. Okay, this is pretty straightforward to understand, hopefully, is if upon looking at these output messages, okay, upon looking at these output messages, if the distance between the message distribution under uniform versus this mixture of the 2 to the k over 2 distributions, if these two are close to each other, then you cannot tell whether it was uniform or not. So I have uniform and I have a collection of mixture of a bunch of distributions around uniform, and you can't tell me which one it is. And if you cannot tell, then that's a lower bound for testing. Okay. So in other words, here what happens is nature is going to tell you that, okay, this is the set of priors, this is the set of distributions I choose, do whatever you want. Even then you cannot test for uniformity. Okay. But what happens for private coin testing? That's where the interesting part happens is, in private coin testing, the way to prove lower bounds will be the following. You actually start off with the channels that the people have selected. Because there is no public coin, the players start by selecting their channels or some distribution over the channels. Okay, so now w to the n is known. Now the way the players are going to select the channels is fixed. Because of private coin, there is no public coin. And now what nature does is it looks at these the schemes that people are going to use as their channels, and then it tries to come up with a new mixture p tilde or a new distribution p tilde, which is dependent on the choice of the channels that the users have chosen, such that for this mixture distribution, you again cannot tell whether the underlying distribution was uniform or from this new mixture. So this in some sense is a maximum problem where you choose the schemes because you have only private coins. You first choose the schemes. Now everyone knows it. And then the nature gets to choose the distributions to fool you. Okay, that's why nature has more power because it's private coin. You choose the protocols, then nature chooses the scheme. Okay. How are we doing in terms of time?
It's 11, but I think we should be good for, I don't know, how much time do you need?
How much do I have? I think less than 10.
We started like 5 minutes late, so you definitely have like 5-10 more minutes.
Okay. Okay. Hopefully I'll be done. Yeah. Okay. So let's, okay, with that in mind, let me just try to give some intuition as to how we are going to capture this notion of how much information you are actually sending across W. Okay, you have chosen W, which minimizes, which reduces the information you can give about Xi, but how are you going to characterize it? Okay, so let's do it with one example. Hopefully that will motivate this information matrix that I will talk about. So we will again concentrate on just the set of distributions that we discussed a couple of slides ago, this plus minus the construction by Paninsky. And suppose we could somehow make inference on a distribution P that's guaranteed to be of the form PZ. If you are able to make an inference, then one could hope that, okay, if you are able to make inference on such a P, maybe you are able to learn the ZIs. So I'm getting samples from the distribution or the messages. I'm able to see the messages. Looking at the messages, maybe I can tell what the values of ZIs are. Okay. So in other words, we have to somehow learn the ZIs. So let's look at when can you learn Z1? What is Z1? Z1 is basically the bias of the first two symbols. When Z1 is 1, then the probability of the first symbol is 1 plus 4 epsilon over k, and second symbol is 1 minus 4 epsilon over k. And when Z1 is minus 1, it's the other way around. Okay. So in other words, if you could learn Z1, you can also know whether the probability of symbol 1 is higher than symbol 2 or not. Okay. And now you can think of it the other way around. If I am able to learn Z1, that means I should be able to tell by looking at the output message whether the input was 1 or 2. Okay. So let's look at this example. Suppose there is player I, and somehow he's promised, or we promise player I that his or her input is Xi, which is promised to be in 1 or 2. It's going to be either symbol 1 or symbol 2, none of the other k minus 2 symbols. Okay. So if Xi is promised to be in 1 or 2, and let's say the channel Wi for user I is fixed, it passes Xi and then observes Yi. What does Yi tell us about Xi? Okay, you know that it's either 1 or 2. When can you know whether it's 1 or 2? Okay, because when you know it's 1 or 2, then maybe you can know whether 1 occurs more often than 2. And using that, you will be able to tell whether Z1 is plus 1 or minus 1. Okay, with that in mind, now see, if Wi of Y given 1 is equal to Wi of Y given 2. So if you see message Y, and it turns out that the channel is such that it doesn't matter whether it was symbol 1 or 2, both of them equally likely output Y, then you don't get any more information about Xi. However, on the other hand, if Wi of Y given 1 minus Wi of Y given 2 is very large, then upon seeing Y, you can probably guess that, oh, maybe the symbol was 1 because it's more likely to happen. Okay, so this is basically the intuition. You can, to know about, so if a message is giving you information about Xi, then these quantities must be large. But now, because of the information constraint, because you have to choose it from a particular set of channels, you cannot make all of these large. And that gives us this information matrix. Okay. So this information matrix is a k by 2 cross k by 2 matrix. And now you can see that these terms are basically what we had in the previous slide. And I'm not going to delve much into it, but the J1, J2th entry basically tells you the relation between J1 and J2. But let's look at just the diagonal entries of this matrix. In the diagonal entries, these will be basically W of Y given to J1 minus 1 minus W of Y given to J1 whole square. So the diagonal entry tells you how much information is this channel going to give you about the jth coordinate of Z. Okay. And this H is a very nice positive semi-definite matrix. It's identity for the identity channel where you don't lose any information. And this matrix is going to be how we are going to characterize all the lower bounds. So because this matrix tells you that if some of the diagonal entries are small, you are not getting information about these, about those coordinates, right? So to define our bounds, we just need three definitions, which is basically the Frobenius norm of a set of channels. So we have script calligraphic W, which is the set of all channels. We have the Frobenius norm of the set of channels defined to be the largest Frobenius norm of H across all channels. Similarly, we have the trace norm and the operator norm. Okay. So for example, you can see that if the trace norm is small, that means the sum of the diagonal entries of H is small, which means you cannot send too much information about all of the bits. Okay. And the idea is that by looking at this channel, it actually captures something called as the chi-square distance between the distributions. Okay. So what is happening in the case? How are what's the way in which the channel is contracting, providing limited information? Let's say you start with a blob of distributions on the left. After you pass this through the channel, the distributions are going to shrink. They're going to become closer by data processing. Okay, how much closer they become is how much constraints you are putting on these channels. Okay, and the amount of shrinkage is basically determines the quality of channels. And we consider basically this distance to be the chi-square distance. All right. So with that in mind, it turns out we can now characterize all the lower bounds that we have in terms of these quantities for the matrices. So we have these matrices that we have defined that actually somehow tell you about how much information you are transferring about the inputs. And basically you can look at these two bounds. On the right hand side, we just have quantities which must be at least a constant. So both of these terms must be at least a constant if you can do public coin testing or private coin testing. Okay, and all the other quantities we know. N is the number of samples, epsilon is what we know, K is the alphabet size. Now this H, W star and H of F, those are actually quantities that we can derive. So in other words, for these right hand side quantities to be a constant, we will need N to be at least this much. And these are lower bounds for public coin and private coin testing. Okay, so once we have that, it turns out that now we can bound the various norms of the matrices. Okay, if you don't have any restrictions on W, it turns out that the Frobenius norm is about root K, because it's basically the identity matrix. So you'll get back all the centralized lower bounds from this. Okay, and we're going to look at public coin SMP in a little bit. But what I want to emphasize here is that those norms of the matrices, you can actually compute them in just a few lines. Those are matrices that characterize, let's say you have L-bit communication or privacy. There are very simple ways of characterizing what's the Frobenius norm, trace norm, or operator norm of all of these channels without a lot of work. And once you plug them in the previous slide, you get all the bounds that you want. Okay. So now in the remaining 1 minute, I think I have, I'll just touch upon interactive protocols. Okay, until now we were talking just about simultaneous message passing. We said that, okay, testing is easier with public coins and so on. But what about interactive protocols? Maybe they can help you a lot more, right? So it turns out that initially when we started this work, we were much more interested in testing because of the fact that for both communication and local differential privacy, tight lower bounds for just distribution estimation or learning were claimed in several prior works. Okay, so for us, the testing was much more interesting and the unified approach was much more interesting. So those are the two things we were thinking about. But unfortunately, during the course of our work, we discovered that all the claims in these papers, they had technical gaps due to several reasons. So basically, we did not have lower bounds for learning under either communication or LDP. None of them were known before. And in this recent paper with Johan and Zitang, we solved this problem and came up with a unified lower bounds method for even protocols that are sequentially interactive. Okay. For testing, however, this year, in the last few months, there was a paper by Amin Joseph Mao and Barrett and Butticha, which look at local differential private testing with interactivity. And they show that interactivity doesn't help beyond public coins. That's also one of the things we observe. And in the same paper, we also have a unified lower bound with interactivity. I'm just going to state these two results. I will not delve into the proofs because I don't have any more time left. But what we can show is even with interactivity, we can prove the same lower bound for learning, is K over trace norm of H. And for interactive testing, we end up with a beautiful quantity. It's not the Frobenius norm. It's not the trace norm squared. It's in fact square root of the trace norm times the operator norm. And this can be always shown to be at most the other lower bounds that we obtained for SMP and private. So in other words, for testing, we have actually possibly 3 regimes. It could be Frobenius norm, trace norm, or this hybrid norm. And you can actually come up with channels where interactivity can help for testing. We have those in the paper. Okay, but it requires very new methods, and there is this very interesting talk by Himanshu, which is 2 hours long, but I think he does it everything on the whiteboard, like he writes on everything. So which you are encouraged to work that talk to watch, which talks about this interactive learning and testing. And this is in one slide, all the results for communication, basically public coin, private coin, and interactive for both learning and testing. And we have, as I mentioned in the beginning, we have several ongoing works on high dimensional estimation problem. And this first work was uploaded yesterday to archive on basically how to prove lower bound for high dimensional estimation under interactive protocols. And we have some recent works on sparse estimation under information constraints and high dimensional signal versus noise detection that was in court this year. A lot of references, some additional references. And the slides are online, so I will stop here. I think I'm definitely 3 minutes over time, maybe 2 if the organizers are generous enough to count it that way. But if there are questions, I'd be happy to answer.
Thanks. Thanks for the talk. So if there is any question right now, you can ask them now. I'm gonna unmute everybody. Otherwise, you can also wait until we are off the record to ask any question. Before that, I actually have one question. So basically, to summarize, that means like interactivity does not help for at least those 2 things, but does help for other things.
Yes. So for communication and local differential privacy, interactivity doesn't help beyond public coins for both for testing, and it doesn't help beyond, and there is no reason to have interactivity for learning at all, because it doesn't even help beyond private coins. Yes, I should have clarified that at the end. Yes.
I have one more question. So
Yes.
are the lower bounds also saying that each player may as well have the same strategy? You have this like max over the channels.
That's a very good question. So I think if each of the player has the same strategy, then you cannot really do much, because what you can show is it depends on the question, right? So if each of the player, we have this paper with Zitong where you can show that if each of the player has the same strategy, then essentially a bunch of distribution will be mapped to the same distribution. Because imagine you're mapping to 1-bit strings. Then if each of the player follows the same protocol, you cannot really distinguish them. So that's why I think in several of our schemes, each player does a different thing in private coin. In the case of public coins, they actually essentially do the same thing because they agree upon the same set S. So I hope that answers. So in private coins, each player, each player shouldn't do the same thing, because then you can't really get much. Because if each player does the same thing, you have essentially a k-dimensional distribution has to be represented by an l-dimensional distribution, or to the l-dimensional distribution, which will lose information.
So yeah, also maybe to label the point. So that doesn't mean that everybody should use the same strategy, but the strategy they should use should have the same kind of norm. For example, one example is in like private coin, SMP, etc. Each player might just like monitor a different element of the domain. So like what they use as the same norm at the end, but it's not the same strategy. They're just they're different, but achieving the same max.
Yes. But yeah, so those are called as symmetric protocols, where each player does the same thing.
Okay, well, I'll take us offline. We can still hang out and ask more questions. But again, Jayadev, thanks very much for giving the talk.
Thanks. Thank you for inviting me.